Right, in this video, we're asked to determine the number of valence and core electrons in an atom. So in my first example, I've got oxygen. So oxygen is right here. And so the electron configuration for oxygen is 1s2, 2s2, 2p4. And the rules for the S and the P block elements, and so S and P block, I'm talking about the S block and the P block, the number of valence electrons are both the outermost S and P electrons. So in the case of oxygen, the outermost S and P's are the two S's and the two P's. So oxygen has 6 valence electrons. And then any electrons that aren't valence are core. So oxygen has a total of 8 electrons. So if 6 of those are valence, 8 minus 6 is 2. So oxygen has 2 core electrons. Okay, if I look at selenium, I see that selenium is in the same column as oxygen. Now, I don't even have to write out the electron configurations to determine the number of valence electrons. All I have to do is count what column it's in, right? So in the case of oxygen, I count the columns, but I skip the D's because the D's don't count, right? So oxygen is in 1, 2, 3, 4, 5, 6. So oxygen has 6 valence electrons. In the case of selenium, it has 1, 2, 3, 4, 5, 6. Also has 6 valence electrons. And notice that oxygen and selenium are in the same column. Elements in the same column always have the same number of valence electrons. So in the case of selenium, also has 6 valence electrons. And selenium has 34 total electrons. So 34 minus 6 is 28. So selenium has 28 core electrons. Let's look at another example on the next slide. Okay, in this problem, we're asked about how many valence and core electrons are there in a cesium atom. So I could write out the electron configuration, but the easiest thing to do is just see what column it's in. So cesium is right here. It's in the first column, so cesium has 1 valence electron. All right, cesium has a total of 55 electrons. 1 of them is valence, so the rest are core. So cesium has 54 core electrons. Okay, now we're asked about the iron atom. Iron is in the D block. So in the case of the S and P blocks, it's the outermost S and P electrons that are valence. In the case of elements that are in the D block and the F block, the valence electrons are the outermost S, P, and D. I'm sorry, I think I just misspoke. It's the outermost S, D, and F. And so in the case of iron, I'm actually going to write the noble gas configuration. So it's argon, 4s2, 3d6. So the outermost S, Ds, it doesn't have any outermost F electrons. So between the S's and D's, it has 8 valence. And if it has 26 electrons, if 8 of them are valence, then it has 18 core. Right? But just like with the main group elements, I don't really have to write out the electron configuration to figure it out. I just count what column it's in. And so in this case, I count any S, D's, and F columns. Right? So iron is 1, 2, 3, 4, 5, 6, 7, 8. It's in the 8th column, so 8 valence electrons. And I've got one more example on the next slide. Okay, in this case, we're asked about europium, which is one of the lanthanides. So europium is down here, number 63. And again, all I need to do is just count what column it's in. So europium is going to be coming from here. So it's 1, 2, 57, 3, 4, 5, 6, 7, 8, 9. So europium has 9 valence electrons. right? If europium has 63 total electrons, then that means it must have 54 core electrons, right? Now, I can also check this with the electron configuration. So if I do the noble gas configuration, I'm going to use xenon as my noble gas. And then it's going to be 6s2. Then lanthanum is going to be 5d1. And then when I go to the Fs, I have 1, 2, 3, 4, 5, 6. So it's going to be 4f6. But when I count my valence electrons, I have 2 plus 1 plus 6, which is 9, which is what we got before just by counting the columns. So I don't have to write the electron configurations. I can just count what column it's in.